last section, we looked at a function called an exponential function. Today we're going to look at a function that's closely related to exponential functions, and that's the logarithmic function. Logarithms used to be the only effective way to make calculations with large-scale numbers. With all the supercomputers we have now, that's no longer true, but logarithms still do have a place in mathematics, particularly in calculus. So let's look at what a logarithm is. Basically, a logarithm is an exponent. These two statements mean the same thing. Let's put them side by side. And you can see that both statements have an equal sign, an x, and a y. But they're arranged a little bit differently. This statement has a 10, and although you don't see it here, we could put a 10 there without changing the meaning of this statement. Because a logarithm is an exponent. So let's look at some logarithms and their values. The logarithm of 1 is 0. And this is asking basically, what exponent do I need to raise 10 so that I have 1? And if I take 10 to the 0 power, we know that's equal to 1. Okay, so 10 to the 0 equals 1. And if I want the logarithm of 0.01, that's -2, because 10 to the -2 is 0.01. If I want the logarithm of the square root of 10, that's 1/2. We know that we can write the square root of 10 as 10 to the 1/2 power. Like so. Pause your video now and work on checkpoint 1. If I wanted to find the log of -25, what I'm looking for is the exponent that I could raise 10 to get -25. But if you think about it, there is no number that I can raise 10 to and get -25, because all powers of 10 are positive numbers. So logarithms of negative numbers and of 0 are not defined. And another way to say that, logarithm domain is x greater than 0. Okay, x cannot be 0, because there's no way I could raise 10 to a power that will give me 0. Nor is there any way to raise 10 to a power that will give me a negative number. So the domain of the logarithmic function is x greater than 0. We can estimate logarithms by looking at powers of 10. For example, if I wanted the logarithm of 359, I know that the logarithm of 100 is 2 because 10 squared gives me 100. And I know that the logarithm of 1000 is 3 because 10 cubed gives me 1000. So if I want the logarithm of 359, I can see that that's in between 100 and 1000. So I would expect the logarithm to be in between 2 and 3. Okay, if I put this statement in my calculator, I find that accurate to 4 decimal places, the logarithm of 359 is 2.5551. If you want to verify this, you can use your calculator to find 10 raised to the 2.5551 power, and you'll see that it's very nearly 359. What happens if 10 is raised to a negative exponent? For instance, 10 to the negative 2 that we looked at a minute ago. 10 to the negative 2 is 0.01. Okay, so logarithms of numbers in between 0 and 1 are negative. For instance, the log of 0.026 is negative 1.5850. When you're working with logarithms on your calculator, the button works just like your power button that we worked with in the last lesson. If you need to push the function button first and then the number for raising a number to a power, an exponential function, you'll need to do the same for the logarithm. If you have to push the number first and then the function button, you'll have to do that same order again for logarithms. Pause the video now and work on checkpoint 2. Just as we used e as a base for some exponential functions, particularly those that deal with populations, the reverse of that is to take the natural logarithm. Okay, for natural logarithm, we usually write ln, and I like to write it in script so that I don't get confused between ln and 1n. So this means natural log, and y equals the natural log of x means the same as e to the y power equals x. Okay, so for instance, if I wanted the natural log of 85, there's a button on your calculator for a natural logarithm. So again, you push whichever one of these needs to come first, either the number or the function, and then enter the other one. So again, to find this logarithm of 85, I'll put in ln 85. My answer is 4.4427. So this is the exponent that I would need to raise e to. I could rewrite this as e to the 4.4427 to give me 85. So once again, these are equivalent statements. Pause the video now and work on checkpoint 3. Sometimes we overthink things a little and we get very dependent on our calculators when we don't really need to be. For instance, if I wanted to find the natural log of e to the 8th, what I'm looking for is what power do I need to raise e to get e to the 8th? Well, of course it's 8. So in a way, the natural log and the e, when they're right together like this, cancel each other out. Okay, so the natural log of e to the 8th is 8. Okay, 10 and e are definitely the most common basis for logarithms, but we can use any number for a base, any positive number. And this is the rule for that. If y equals the logarithm to the base a of x, then I know that a to the y power equals x. These are equivalent statements. To remember how these work, I remember this. The a is the lowest number over here. And by lowest, I mean the furthest down the page. And also over here, it's the base of the exponential function. The x and y switch places. Okay? The x was over here with the a. Now the x is by itself, and the y is over with the a. So x and y have to switch places. A stays down at the bottom. How would we graph a logarithmic function? We've already talked about the fact that logarithms are not defined when x is a negative number or 0. And remember that the exponential function looked like this. Came up here through this point, 0, 1, and went on its way. The logarithmic function has a very similar shape. And this time, instead of not ever touching the x-axis, this function never touches the y-axis. It also crosses an axis at 1. And so if you could take this whiteboard and fold it up, along that line, these two functions would match up. Let's look at some examples of exponential and logarithmic statements that are the same. If 3 squared equals 9, then I could say the log base 3 of 9 equals 2. So what I'm saying is, what do I have to raise 3 to get 9? 3 squared. How about 1/5 to the negative 2? That equals 25. To write that as a logarithm, I could say log to the 1/5 of 25 is equal to negative 2. Okay, because 1/5 to the -2. The negative means I'm going to flip it over and get 5 and then square it. If I were to say 10 to the 5th is equal to 100,000, I could rewrite that as a logarithm. Log base 10 of 100,000 is 5. When we're writing about log base 10, it's perfectly acceptable to leave the 10 out. If there's no base indicated, we just assume that it's 10. Let's look at a couple more. If I say 4 to the -3 is 1/64, I could rewrite that as log base 4 of 1/64 equals -3. 2 to the -4 is, it's 1/16. So again, here's my bottom number. That's going to be my base. Log base 2. And the -4 was with the 2. So the 1/16 is here now. -4, not -1/4. Okay, now let's look at e to the 0 equals 1. We know any number to the 0 power equals 1. So I could say log base e of 1. And you can write it this way. More commonly, it's written as natural log of 1. Both of these equal 0. Okay, because e to the 0 power is equal to 1. Okay, let's look now at some properties of logarithms. I think you'll see that they have similarities to the properties of exponents. Again, log base a of 1 is 0. Log base a of a is 1. Log base a of a to the r is just r. And a raised to the log base a, it's written very small. Log base a of x equals x. So again, we saw earlier that, natural log of e, these cancel each other out. If they're written this way, a raised to the log base a of x power, these cancel each other out and I get x equals x. Okay, so just some properties of logarithms to keep in mind. Let's look at a few more properties. If I have a log base a of xy, I can split that up into the log base a of x plus the log base a of y. Remember that a logarithm is an exponent. And just like when we have, 2 squared times 2 to the 3rd, we make that 2 to the 2 plus 3. So when I combine these, I add the exponents. So when these are already combined, I've added the exponents. Remember that a logarithm is an exponent. Okay, we call this the product rule. Okay, we also can say if I have log base A of x over y, we have the quotient property, which means I've got log base A of x minus log base A of y. Okay, and this is the quotient rule. And the final one I'm going to show you is probably one of the most useful ones when we're trying to solve an equation where there's a variable exponent. So if I have log base A of x to the r, I can rewrite that as r log base A of x. So if I had the r that I didn't know, it's very difficult to solve for an exponent, but if I can take the logarithm of it, then I can bring the r out front here. Now it's not an exponent anymore, and much easier to work with. One of the things we use these properties for is to rewrite logarithms as a single logarithm, or sometimes we want to split a logarithm apart. Maybe there's one part that's easy to solve, and we want to isolate the part that's not so easy to solve. So let's look at some examples. Let's say I have log base A of x plus log base A of x minus 1. When I'm adding these two logarithms, I can write it this way. Log base A of x times x minus 1. Okay, there's times when this form is more useful. There's other times when this form is more useful. But the point is to remember that either form is equivalent. So if I had log base A of x squared plus 4 minus log base A of x plus 6, I could rewrite that log base A, and now I'm going to divide x squared plus 4 over x plus 6. Okay, and just like in other properties of math, addition, the order is not important. I could add one to the other either direction. Subtraction order is important. Whichever logarithm is listed first needs to be the numerator of my fraction. Okay, the second one is going to be the denominator. Let's look at one more example. In this case, I cannot combine these two like I did up here because I've got this 5 out front. What I can do is use the power property, and I'll rewrite this as log base A of 9 plus log base A of x to the 5th power. I can bring this 5 out here and make it an exponent. And now I can combine these two and get log base A of 9x to the 5th. Pause the video now and work on checkpoint 6. Combining logarithms can also help us evaluate logarithms if we know just a few specific values and can combine them to get what we want. For instance, if I know that the log base 6 of 7 is approximately equal to 1.09 and the log base 6 of 5 is approximately equal to 0.90, I can find the log base 6 of 35 by breaking that 35 down into the two things I have. So log base 6 of 7 times 5. And now with that product, I can break that down into log base 6 of 7 plus log base 6 of 5. So I would have then approximately, from up here, 1.09 plus 0.90, so 1.99. Okay, let's look at another example using these same two values. I have the log base 6 of 5 over 7. I could rewrite that as the log base 6 of 5 minus log base 6 of 7. And again, substitute my values in. This is 0.90 minus 1.09. And when I do that subtraction, I get negative 0.19 for my answer. And this makes sense because I'm taking the logarithm of a fraction, number between 0 and 1, so I would expect to get a negative answer. How about log base 6 of 5 cubed? Now I'm going to use my power rule and move the 3 out to the front. I have log base 6, I'll move the 3 out to the front, of 5. And log base 6 of 5 I know is the 0.90, so I'll have 3 times 0.90 or 2.70. Okay, and a couple of easy ones here. Log base 6 of 6 would be 1. And the log base 6 of 1 would be 0. So by knowing just these two facts, I could do several things without even using a calculator. Pause your video now and work on checkpoint 7. In the last example, I gave you a couple of values for log base 6. But if you look on your calculator, there isn't a button for log base 6. The only buttons we've got is log base E, or natural log, and log base 10. So what do I do if I need those values and they're not on the calculator and I don't know what they are? we can find them by using change of base formula, which looks like this. I have the log base 7 of 3. I can rewrite that as the natural log of 3 over the natural log of 7. So this is approximately 1.0986 over 1.9459. And when I do that math, my value is approximately 0.5646. Okay, if I need to check my work, which is always a good idea, I can try 7 to the 0.5646. This is something I can do with my calculator, and it should come out very close to 3. And in this example, I used natural log and natural log. It's also permissible to use log base 10 and log base 10. It'll work out the same. These numbers will be different. This number will be the same. Earlier, we talked about the fact that there was a relationship between the exponential function and the logarithmic function. Let's graph those again. This time I'm going to use the natural log function and e to the x. So for the exponential function, e to the first power is 2.718. So over here 1, I'm at 2.7. E to the 0 would be at 1. And I can just kind of sketch that in there. As we saw before, the natural log function is going to cross the x-axis right here. It's never going to cross the y-axis, so it's just going to curve down this way and out this way. And once again, we see that if I just ran a line up this way, that these two functions would match up very nicely because they are inverses of one another. Pause the video now and work on checkpoint 8. At the beginning of this lesson, I talked about how some uses of logarithms are no longer really applicable, but we do use them in some real-life situations. Let's look at one. Annual U.S. power generation from wind in million megawatt hours can be approximated by this function. F of x is equal to negative 335.5 plus 193.1 natural log of x. And we're going to say that x equals 6 corresponds to the year 2006. Okay, and given that, we want to find the values for 2008, 2012, and 2015. So to do that, just use this function, very simple. The first one, when I put an 8 here in place of the x, I get about 66. When I replace x with a 12, I get 144.3. And for the year 2015, my number is 187.4. And if you recall, when we were working with an exponential function, that the numbers changed very rapidly. But for a logarithmic function, it is continuing to grow, but it's growing at a much slower rate than an exponential function. This concludes this lesson. You should be ready now to work on your homework assignment.